Today we're going to continue work with our summation notation, so we need to remember that the nth partial sum is the sum of the first n terms and the notation that we've been using for summations. Here is a list of properties, some of which we've already looked at, but we haven't necessarily defined. So the first one, C, is a constant. So we know that if we're summing from 1 to 7 and we have a constant 2, we would multiply the 2 and the 7 together and get our answer. We can split sums, so if we're adding or subtracting, then we can add or subtract each individual summation. If there's a constant times your term, you can pull the constant out front. And then the last three are three properties that we'll use in a moment, but definitely need to be memorized, okay? So if we just have our index, then the sum is n times n plus 1 over 2. If we're squaring that or cubing it, then we use these other formulas. So these are very important. So now let's go ahead and look down at our examples on how to use this. So we can break this into several parts. All right, so we know that the 2 can come out front. So we have 2, the sum from k equals 1 to 5 of k. And then we can break off the 9 and say minus the sum from k equals 1 to 5 of 9. Now for the first summation, we are summing our index as we can see in this property, that the first one that's highlighted. So we'll have 2 times the quantity n, which is 5, times n plus 1, which is 6, over 2, minus, in the second summation, we are summing a constant, which is this first rule. So we will just do 5 times 9. So then we multiply, do the arithmetic, we get 30 minus 45, and our answer is negative 15. Okay, in the second example, we have a 3 as a coefficient again, so we'll pull that out front. We have k equals 1 to 4 of 2 to the k. We don't have a formula for that that's listed above, so we'll just go ahead. It's only 4 terms. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. And then we multiply and add, and we get 90. All right, in the third example, we first need to write it as a summation. We see that this is a list of perfect squares, so I equals 1. 196 is 14 squared, and this is I squared. And then we'll go ahead and use the second starred rule. And so that summation would be 14 times 15 times 2 times 14 plus 1, so 29. All of that is over 6. So I will give you a calculator for computation, but I will also expect you to write out all of these properties so that I know that you're using them correctly. So we'll get our calculator for the computation part of it, and we get 1015. But I want to be able to see this step here to know that you know the property, all right? Okay, the last 2 examples ask us to write these in sigma notation. So there's 4 terms here. So we'll start with our epsilon. We'll say I equals 1 to 4. And then we look at the terms in this series, and we see that each term is varying by 5. So we know that it is an arithmetic series. So we'll write the definition for an arithmetic term. So we would say 3 plus 5 times, not n this time, but I, because that's what we're counting by, minus 1. And then generally in summations, we go ahead and clean that up algebraically. So we would say -2 plus 5i. In the arithmetic sequences, it's fine to leave it as it is in the first line, but in the summation, we go ahead and simplify. Okay, for our last example, we want to write S10. So again, we're counting. This time I'll use K. It doesn't really matter. From K equals 1 to 10. We look at the terms here, and we see that this time it's geometric because each time you're multiplying by 3. So we can go ahead and use the formula for the for the geometric sequence, which is A1 times R to the n minus 1. And again, since these have a common base, the 3 and the 3, we can use our properties of exponents to simplify our expression in the summation algebraically. And we just get 3 to the, oh my gosh, K. I don't know why I wrote N. But at the top, I should have written K here as well. All right, let me know if you have any questions.